So as promised, I'm going to do a whirlwind course summary so that I can leave time for any questions that you might care to ask before the survey. We do have to end a little bit. We do have to end early for that purpose, but we'll have a few minutes to ask questions. So here's some information. I hope it doesn't contradict anything that I said earlier. But in any case, as usual, the auto grader will be running once a couple of times before the project. The benefit of those of you who get done early, and then it will run continuously after that. Okay, and please do make sure those of you who need alternative finals, and that includes people who have told me before that they're, earlier in the year that they're going to need an alternative final. I should talk to all of you, or I should hear from all of you so that I have a complete list of who's going to be affected, and I can check to make sure I get a time that will work for as many people as possible. Okay, so let's just go whipping through here. What have we done this semester? There are, so it's sort of half and half. Well, from my point of view, it's half and half because you're the people who work on the projects. But as far as lecture material is concerned, we've been talking about programming languages, or at least features of programming languages, and their translation. And from the point of view, but there's also a practical aspect. This course has an agenda, which actually could be fulfilled by things other than compilers, but compilers are useful because they are large and complex systems. And so in the process of actually building one or pieces of one, you get some exercise with handling complex software and the tools that are available for doing that. So what topics did we talk about in programming languages? Now, the purpose of these slides, of course, is just to remind you of things that should be familiar to you by now. So we talked about the concepts that we talked about that apply to lots of programming languages are such things as scope, meaning what it means for what a declaration means, what extent it has, or where it has effect, I should say. We contrasted this with its general concept for what do things mean in a program, and we contrasted this with their lifetime, which is a dynamic concept, namely this is where a variable is visible, this is where you can use it, that's scope, this is how long, this is the period of time in which it lives, that's its lifetime. And we did a lot on the interaction between programming languages, lecture time anyway, the interaction between programming language feature and implementation. So we talked about, for example, the representation of functions and how this is affected by the features in the language. So you have recursion, you have simple Fortran, which didn't have any recursion, and basically everything could be static, didn't have dynamic data. Then when you add recursion, all of a sudden there have to be some fairly substantial changes in your strategy. When you add data that doesn't have to be static sized, well, that's another complication. When you add function values that are especially function values that are not just simple things, where you at the outer level, but are pointers to nested functions, things get even more complicated. And then when you add inheritance and object-oriented programming, well, all of a sudden you've got this whole other mechanism that you have to add. I didn't put on this slide, but there's also exceptions, for example. What effect does that have on language design and representation, I should say? Now, we talked a bit about formal methods for describing languages, a bit, not very much. So in the case of most of that was in syntax. So we have a way of describing formally in sort of a mini language, if you will, BNF, describing one aspect of programming languages, namely their syntax. And we also saw a brief introduction to a notation, not the standard notation, but it's a notation, a formal notation for describing type systems, which I formulated it in Prolog. But the idea is, this is a way of describing declaratively what the type rules are for a language, rather than simply relying on an English description, or for that matter, just giving you the program that checks these types and saying, here, that's the definition. Okay, so then we talked in general about the steps in translating programming languages, and by this time you should be familiar with them. It's a sequence of translations, starting from text and ending with either execution or executable file or some intermediate form like a Java class file. And what you see here is a list of the various major topics in each of these areas. We had context-free syntax, basically handling the structure of a program or determining and extracting the structure of a program without any reference whatsoever to what any of it means. Static semantics, where we figure out what names are defined by what declarations mostly, and we determine also as much as possible, depending on the language, and there's interaction between language and compiler here. We determine as much as possible whether the program is consistent, whether you have in fact met all the type rules and other rules of the language. Then we talked a little bit about, we went into code generation, sort of the basic idea. It's pretty simple really, but in essence what you're doing is you are doing a partial execution of the program. That is, you're traversing a tree, and you're saying not what should this do, but what are machine instructions that would do this. So it's sort of a different take on execution, but it's really the same idea. It's a traversal of the program. And we went through these examples of particular mechanisms within programming languages that each of which has its own implementation considerations, exceptions, procedure calls, object-oriented methods, and garbage collection. These are sort of major features of programming languages these days. And then just a taste of optimization, what it means, how you can. This is further analysis of a program to determine, or in this case, generally of the intermediate language of a program, to determine ways that it could be improved. Now, up there at the top, I say code generation intermediate forms. The idea behind the idea of an intermediate form is to basically factor the code generation task into that part which is specific to a particular machine, and that part which is which is generic over all machines. So, with properly done and interfaced to a virtual machine, an intermediate form allows you to write code generation without thinking without thinking too much about the machine at the end, and it allows you to write machine code generator without thinking too much about the language that you're compiling from. It's a basic software engineering principle, and we didn't see the real benefit of this in this course, the major benefit in this course, which is, as I mentioned earlier, or as I mentioned in the previous lecture, which is that you are now able to have a single compiler, a single front end for a language that will compile code that can then with relatively small effort, be converted to machine language for a large variety of different machines. Now, in the process of doing the project, we came across a few tools that are that we use all the time in, or well, especially the last one actually, but that have uses all over the place, namely programs for generating lectures, parsers, programs for taking these high-level specifications, these formal specifications of syntax, and converting them into programs so that you can write things in a language that is natural for the problem you're solving, namely figuring out parsing the grammatical structure of a language, and at the same time, without having to actually write by hand programs to do this. And throughout the year, although this has been a hidden thing that we haven't really talked very much about, you've been using a version control system. I hope in the process that some of you have got enough experience with this by this time that you get it. You know, when you go into industry, for example, you will understand what's the importance of this particular tool. And of course, as you know, being in the middle of it at the moment, we did an awful lot of construction of complex software. So what I'm asking you to do is to be, by the time you're finished, and the reason, by the way, for that paper that I asked you for, or asked your groups for, was in part it's an exercise in exposition, technical exposition, but in another part, it's to get you to go back and look at all of this, program that you're doing, and to try to understand it as a whole, so that you aren't just blinkered in on a particular phase of the program. So what did we do? I mean, there are various tools that we use to keep ourselves sane. One of these is, or should be, I should say, the concept of a pass, that you can actually do things in pieces. You can break a task down into smaller pieces, and especially in this case, we can do things in a sequence of phases, or passes, that each of which is much better defined and much easier to hold in your head at one time than the whole thing is. And likewise, that's actually the third bullet, has to do with this use of object orientation to partition a task. There are generic things that you will be want to do to each node. I hope by this time people are starting to get the idea that the way that you can deal with this is that there are common patterns that you use for generating code that basically differ in detail by what kind of thing you're applying them to. So, for example, if you're doing an assignment, then if you're processing an assignment, then the first thing you do is you have to generate the code to evaluate the right-hand side. So you've partitioned this into evaluating the right-hand side. That's a generic operation, and then actually doing the assignment. And by identifying generate code to evaluate as a separate method, you realize that you can simply express this as generate the code for my child, and then do whatever special stuff I need to do in assignment. And this is an idea. This idea of dividing up, of abstraction, is very important, and you get a lot of chance to exercise it in this project. Now, I don't know how much from some of the comments, I'm not sure that people quite appreciate the uses of intermediate forms, but okay. I mean, at least I provided a chance. I think that those people who have taken this seriously probably have made things a lot easier for themselves than those of you who have tried to generate IA32 directly. But I don't know. That has yet to be seen. Okay. So this is, everyone thinks of this. Students tend to think of 61A as a scheme course and 61B as a Java course. And let me tell you, it drives us crazy when you do that. And they tend to think of this as a compiler course because you spend 26 hours a day writing a compiler. So, of course, what else could it be but a compiler course? But I'd like you to take away the notion that the things that we've talked about here are general purpose tools. There are many languages lurking in just about every problem that you solve. People who have done, for example, people who have done, who build game software find themselves eventually building themselves game engines, which are in effect sort of compilers for games. You have your own mini language for describing scenes and that kind of thing, and it's a very natural thing to do when you've got a large and repetitive, a large project to do that has repetitive portions, things that recur over and over again. Make a language to describe it. You will be more concise, and it's easier to get it's faster to get things done once you have the language anyway, and it's a very useful thing. And in doing this project, for example, maybe some of you, I notice in doing this project, some of you caught on to the idea of doing a little pre-processing, of having programs that write programs, so that some piece of the program, some piece of the problem which you can that you can split off, you can think of as requiring a mini language, like for example parsing or lexing. The same idea can apply all over the place. If in a large project, you can find all kinds of applications for what is essentially simple translation. So there's a theme these days. It's called domain-specific languages or little languages, where you're tooling along and you say, this is getting kind of tedious. Why don't I just write a little thing here that will where I can express all of this more concisely, and it will do all the programming for me. And you end up doing that. When you get into the habit of doing that, you soon find you can produce some rather elegant effects. All right, now as for those of you who are interested in going on in research, there's plenty going on these days. For the last several years, the big thing has been parallelism and distributed computation. How are we going to deal with multi-core? I mean, you hear this multi-core. The single thread program is dead. Long live the multi-threaded program. This is a recurring theme, and for various reasons, both commercial and physical, and so the question of how you compile for this is coming back into has really floated up into the agenda. So there's a lot to be done there, and what languages should we have, what compilation techniques do we need. And then a lot of stuff has gone on in the last few years in static program analysis. I should tell you, back in the late 60s and 70s, people got all excited about the idea of program verification. This was basically static analysis of a program with an eye toward answering the following question. Does this program actually produce the following output with the following properties? So you give a spec, which is what the program is supposed to do, and you ask, does the program do that? And it was observed that with a little work, you can convert a program into a theorem, into a mathematical theorem, which, if proved, demonstrates exactly this property. Unfortunately, theorem proving is undecidable in general, so they had merely turned one difficult problem into another, they did make some progress in proving those things that could be proven. It didn't, however, get very far. The programs that you could prove were pretty small. And so this got abandoned in the late 70s. And it was only later, starting in the 90s, that you started to see people saying, well, maybe we can't prove entire programs, but maybe we can use these techniques that started back in the 60s and 70s and push them further and work on particular questions about programs, like, will there be null pointer errors? Will there be races? Is this malicious code? Is this trying to do something malicious? And these sorts of automatic determinations are a big thing these days. They also, of course, the same sort of analysis allows you to answer questions like, will these two threads access the same variable simultaneously? That's another static analysis, which obviously has applications to parallel processing. So this is all an area. That that's been going on for the last decade or so, decade and a half, and it's a big thing. So these are sort of research areas in this, or research topics in this, general research topics in this area. And let's see, those were my parting remarks. Okay, so that's it. A whirlwind overview of what we've done in this course, perhaps much to your surprise in some cases that we've done this. But it's a fair warning so that you can be ready for the test, if nothing else. And now, in response to request, I'd like to throw the floor open for any additional questions you might have before we turn things over to the HKN representative. Is the HKN representative here, by the way? HKN, are you here? Yes? No? Well, if he doesn't come, he doesn't come. Okay. What? Okay. Go ahead. Ask. I'm here. Yes?
Can you give us your take on the editor war?
Pardon me?
Can you give us your take on the editor war?
The editor war?
What are you done?
Are you out of your mind? Don't you know that this is religious? I mean, I've always thought that the fact that people use VI is proof that this is a purely religious question that you shouldn't worry about. So you know what my preference is. I will only say this. I think that there is a tendency to, with every new system, every new IDE seems to bring in with it a new editor. And I think that's a bad trend. There's a tendency here there's a tendency of the community to stand on each other's toes rather than on each other's shoulders. And this is one example. The recreation of editors at every turn. So the result is that you have forums in which editing is used, like, for example, on the web, where web browsers provide what is, in my opinion, a rather poor editor interface. That's a rather bad way of generating content, because they started from scratch, and Eclipse started from scratch, and it's as a result we get this new kind of editor it's big and bloated, and it really could have been built on top of existing editors. Most, by which I of course mean mostly Emacs, but that's my preference. Yeah. Yes, Justin.
Can you explain high-level JITs?
High-level JITs? Well, JITs in general. You remember that when I talked about optimization, I talked about conservatism in the optimization. That is, there are certain things that you cannot know statically. One of the things, for example, and this includes not only questions such as, is this a constant, or what constant is this, but also questions like, is this code, in practice, is this code going to get executed very much? And the result of this is that more and more, and there are other reasons too, but for more and more, people have turned to a different style or paradigm, I guess, of programming language translation, in which one compiles to an intermediate code of some kind, of some description, and that is the form in which you store and distribute programs. And then, at the right moment, then as needed, this code can be both interpreted, or it can be further compiled and optimized on the spot, when in fact you have more information available to you. Like, for example, you have some profile data about how often something gets executed. And now, because and also because the compilation steps, the optimization step is generally slower than generating simple-minded intermediate code, you can actually produce these things. You can produce these things faster and not waste time in your compiler on optimizations that aren't going to be used. So for all of these reasons, and finally, intermediate language code can actually be more compact, a bit more compact than machine code in some cases. So let's see what other. Oh yes, there are other advantages. At execution time, when you've actually got the code in hand, it's easy to do inline. It's easier to do inline expansion. Think for a moment about what happens if you. I've defined a function. I put a function in a header, which is just the signature of the function, and I call it here. So I have a bunch of calls to this function. Later, I go and I implement the function. Well, can I do inline expansion, which might be advantageous? Well, no, because I've got the compiled code over here, and I only later compile the function that it calls. But with a just-in-time compiler, you can do inline expansion at the last minute. You can do it at execution time. So I mean, there are lots of advantages, like lots of reasons why you might want to delay compilation until just in time, right? Until it's actually needed. An early experiment in the early 1970s by a fellow by the name of Hansen at the University of Waterloo. He took the Wat4 compiler, that was the Waterloo Fortran compiler, which was basically intended as a student compiler. You could put things in, and it would run them in batch mode and execute them quickly. He took this, and what he did was he changed the compiler so that, in fact, it would start out by interpreting. It would generate an interpreted interpreter output, or intermediate language. It would start out by interpreting this thing. After it had interpreted a basic block a certain number of times, it would pause and compile it, just like a JIT, basically. And then if it executed a few more times, it would optimize it. It would do some sort of local optimization on the thing. And as a result of this, he got a compiler where the end-to-end processing time, that is, between sticking in the program at this end and executing it and getting the results out at this end, was reduced both from a compiler that did a straight naive translation and execution, and also from an optimizing compiler. So it was faster than an optimizing compiler when it came to compilation, and got similar results on execution because it eventually did optimize the code, and it was but it only optimized those portions that really got used, and it was faster than also faster than a code generating compiler because it generated a more compact intermediate form, and also it generated code that would run faster. And so that example I guess was the prototype for a lot of things that came to come. And basically the advantage is this portability. You can port things once you can compile things and then port them in their compiled form very easily, and you can take advantage of runtime information. So that's sort of the idea behind these JITs. Yeah.
What are your thoughts on
Haskell? Well, it's an interesting language. I predict it will you'll see more of it in the future because functional programming languages there are obvious applications of parallel or multi-core programming to functional programming languages. The reason being that you don't have this problem of multiple threads modifying something. You instead have nothing gets modified once created, and therefore you are freer. It's more. It takes less analysis to do parallel processing on these things. So for these reasons, it will become interesting. It has an enthusiastic niche. I don't think it's really broken through into industrial practice very much, but it continues to be, from my point of view, a very interesting side of programming languages. Fun to work with. Yes.
favorite Gilbert and Sullivan opera?
Ha! Well, now that's very interesting. What would be my favorite Gilbert and Sullivan operetta? Well, I have a special place in my heart for Ruddigore, since I've performed both in straight Ruddigore and in a parody of it. I think that Princess Ida is kind of tuneful, and I've also been in a parody of that called Princess Ada, but. The Ruddigore parody was also Ada-oriented. In the original Ruddigore, the Baronet of Ruddigore is cursed. He has to commit one crime a day, or die. And in the parody, I played William Murgatroyd, who. You don't seem to get it. All right. Well, anyway, who was the CEO of Microjunk Technologies, and who was cursed with having to put one bug into his software every day. And, so it was kind of interesting. I think we have now. Is that HKN up there? Yes. Okay. Fine. I think we have time for another question. Yes. Graphical programming language? You mean, you mean, yeah. That's an idea that's been around for a long time. It's been reinvented many times, and one might well ask why it is that it hasn't stuck. I think the problem is, from my point of view, that it doesn't seem to scale very well. So it's useful for I find, for certain applications, like for example building GUIs, where it's sort of what you see is what you get. There's a great application for it there. If you're throwing together very simple things, then that involve data flowing all over the place, then the graphical structure really captures the bulk of what you're trying to convey. Then it makes sense. But I have to say that for general purpose programming, I've never been terribly impressed. That's maybe it's because by this time I've learned to deal with text so well that it's like it's kind of like I attended an HCI talk and about helicopters. And the sorts of visual aids that you might give a helicopter pilot. And it turned out that the experienced pilots, these things really helped some of the less experienced pilots. The experienced pilots found that they just didn't use the information because they already had figured out in their heads or whatever their instincts how to what they needed to do in various situations, and I think maybe I've been spoiled by the fact that, or ruined or whatever, by the fact that having grown up in the age of text, I am now able to handle that, and it conveys as much to me as graphical things ever did. So that's basically the problem. I think it's an interesting idea that just doesn't scale, and that in anything I've ever seen. All right, I think I'm going to have to turn this over to HKN. So thank you all for your attention, and I will be available to consult on the project as usual. And I hope in the meantime that you enjoy yourselves.